My paper is Dynamic Shadow Rendering with Shadow Volume Optimization. There are four aspects to it. First, shadow volume is utilized expensive for real-time rendering applications, which includes updating volumes and calculating silhouette edges. Second, shadow effects can help viewers to perceive the relative distance and the position of objects, as well as the geometry of occluders and occludes. Third, rendering realistic shadows is difficult, and doing it in real time is even more complicated. Fourth, offline rendering techniques such as ray tracing can generate shadows automatically. Nonetheless, no standard approach to real-time shadow rendering currently exists. Existing techniques. First, existing shadow volume methods are CPU-intensive and complex occluders result in poor rendering efficiency. Second, among numerous shadow rendering methods used in the various applications, shadow volume has been prevalent and is efficient in its ability to generate accurate real-time shadows. Third, when compared with shadow mapping, with its aliasing artifacts problem, shadow volume is considered the better choice, especially when there is a demand for high-quality shadows. Fourth, nowadays, graphics cards with substantial test support are omnipresent in the current computer hardware market. Fifth, efficiency of shadow volume algorithm is limited to two main procedures: determination of silhouette edges and shadow volume rendering ultimately determines the shadow rendering time. Sixth, 3D games have become prevalent, propelled by concomitant sharp increase in the usage of smartphones and tablets. Seventh, the graphic hardware is in smartphones and tablets is resource-constrained, and so efficient implementation of dynamic shadows for 3D games and other 3D applications is crucial. The contribution. First, introducing a hashcoding method that greatly improved shadow volume time efficiency by reducing silhouette edge processing time and shadow volume restoration time. Second, reducing hardware dependency of shadow volume to make it practical for an embedded system to run real-time shadows. Third, gaining the possibility that using the hashcoding method with other shadow volume culling and clamping method to further improve real-time shadow generating efficiency. The left is shadow volume created by single-point light and square occluder. The left is basic procedure of state-path algorithm. We propose a hashcoding shadow volume algorithm that improves the efficiency of silhouette edge determination. In the proposed algorithm, according to the position of the light source and the mesh, all the faces of the mesh are tested to determine if they are front surfaces. Next, for all the front surfaces, silhouette edges are recorded and each silhouette edge is extended away from the light source to infinity to form a shadow volume. We use shadow polygons to refer to polygons that form the bounds of the shadow volume. The efficiency of the search for the silhouette has a significant impact on the overall efficiency of the algorithm because it is the most time-consuming step. figure demonstrates the rendering pipeline of our method, including loading vertices data, rendering model with ambient lights, searching silhouette edges, rendering shadow volume, and doing stencil tests. Finally, blending shadow color to draw shadows. We implement our proposed algorithm in C++ with OpenGL and conducted timing tests on a PC with an Intel i5 3210 2.5 GHz CPU and an Intel 4000 HD graphics card, 8GB RAM. In our implementation, all scenes were rendered with a resolution of 800 × 600 pixels, 16-bit RGBA color buffers, and 8-bit stencil buffers. For each scene, there was a single point light source in a distinct place, and the same floor was used to conveniently observe shadows. We also implemented our method on several smartphones and tablets. However, timing tests are conducted on PC. In the implementation, JPass was used to perform the stencil test, and when viewport cut through shadow volume, JFill was used to obtain correct results. The pseudocode for our implemented hashcalling method is shown. The scenes on PC with different meshes from left to right. The first is 25 DWAFs with 47,400 triangles. The second, chains with 7,128 triangles. Third, airship with 8,698 triangles. The last one, a chlorine box with 19,490. From the graphs we can see the left is per-triangle method, the right is hashcalling method. The improvement of our algorithm over the classic algorithm is evident. Using the hashcalling algorithm, the triangles that had to be rendered for the shadow volume decreased sharply without any additional burden on the CPU. As a result, the FPS of each scene significantly increased to a new level. Test scenes of a manifold and non-manifold meshes. Despite the number of scenes rendered using our proposed method on smartphones and tablets, because one of our targets is to efficiently render dynamic shadows on smartphones and tablets. Reducing hardware dependency can help algorithms to become more robust. We have three conclusions. The first, a hashcalling shadow volume algorithm that can generate real-time shadows, even for relatively complex meshes. The second, the implementation and the test results. Our algorithm improves the performance of various kinds of things, irrespective of whether the mesh is simple or complex. Third, improved performance primarily by simplifying silhouette edge determination, resulting in reduced shadow volume rendering time. Thank you.